Hey there. In this video, I'm going to talk about something which is very crucial in the context of incrementality testing that has become very popular and is pretty much in vogue these days in performance marketing domain. And that is, when do you exactly stop an incrementality test? So incrementality test is becoming, everyone is doing it, but there are certain aspects to it which have to be remembered. There are certain considerations, there are certain assumptions, and one important point is when to actually stop it, right? So obviously, where exactly you will do it, what jaws you will choose, those are there, but it's also equally important to know just how long you should continue. Well, because if you stop it too early, that can actually become a problem. So what you see in front of you is a graph that actually shows the outcome of such an experiment. So you have the days of the experiment. So the experiment started on day 0 here, as you can see on the x-axis, and these are the days into the experiment. And in the y-axis, you have the cumulative lift percentage, like how much cumulative lift has actually been generated, in course of this in course of this experiment. So we are talking about a marketing experiment. It can be pretty much anything which has two variants, so control, and then you have the test. So you'll see that control A and variant B. And if I just jump into the code here, this of course is simulated data. So we have conversion rate as a metric that we are basically measuring, and we are talking about two different kinds of days. So over a week, you can actually have weekdays and weekends, right? So the thing that I'm trying to establish here is that if you only look at things like the statistical significance, which are obviously very important, but if you only look at that, whether or not the sample size has been reached, there is a required sample size for any experiment, and the statistical significance usually given by things like p-value, if those are also satisfied, even then it may not actually be the right time to stop an experiment. That is what I'm trying to say. And there can be several reasons for that. One of the most important reasons that I've talked about here is actually the day of the week effect. So you see that this actually started, the experiment started on a weekend, as you can see by this blue patch here. And obviously it repeats every 7 days, and you see that it started on the weekend. And the way this experiment actually has been set up in this dummy example is by setting a very high number of users per day. So it, at the very start of it, and that can actually happen because of something called a novelty effect. Like if you start something new, suppose it's a brand which already has a lot of either brand loyalty, or it is well established. So you'll see that the number of users per day has actually been set to 30,000, which is a pretty high number, right? So somewhere down here you will actually see that the number of users per day has been set to 30,000, which actually makes it very interesting, because the required sample size from this analysis, as you can see, effect size for proportions, Cohen's age, and power analysis, from there we get that effect size, and from there we actually calculate the sample size per group. So the sample size, as you can see, is 17,000, somewhere around that, which is lesser than 30,000, which therefore is attained on the very first day itself, right? Because that's 30,000 is the number of users per day. And since it has crossed 17,000, it is past that number, you actually know that you already have statistical significance on the very first day itself. Okay. And this basically means that your statistical significance, in fact, you, if you go on to do another thing which is called um the chi-square test, which is where you actually get the p values from. Okay. So chi-square is simply given by this z square, which is the z score, and this is given by this formula here, and you'll get the outcome of this. And in this case, we actually saw that the statistical significance was reached on the very first day itself. Okay. And so now the other thing is, how do we calculate this cumulative observed lift? So what we are basically observing here through this blue line is the cumulative observed lift. By cumulative is simply meant the cumulative average lift. Okay. And you'll see that this graph is actually going down, went up again a little bit on the weekend, but it's nowhere near the previous case. And the reason is because it's basically cumulative. So the conversion rate is nothing but the number of people who are converting relative to the number of users getting added, right? So if we actually look at this number here, so this is being basically the the number of conversions is basically getting is following a binomial distribution. Okay, so the binomial distribution has two arguments in it, two parameters. One is the number of users, which we saw is 30,000, and the other is basically whether or not which is a sort of a true or false. So it's a binary, so whether it's a weekend or it's a weekday. So you can see the expectation is given by np and variance of x is given by np1 minus p. These are all properties of the binomial distribution, and from there we actually are able to utilize these values in the next steps. And if we calculate the lift curve that we actually plotted, so this is simply given by, if I go to an example here, you will see that it's given by the total number of conversions. So this is two variants, right? One is the control, another is the variant b. So in each case it's just the number of conversions up to a certain day divided by the total number of users up to that day. So essentially what's happening is you are obviously taking the numerator, the number of conversions happening till that day, but you're also taking into account the number of users. So the number of users every day, 30,000 is getting added. So you can understand that the lift is actually going to decrease, the cumulative lift, because you're getting more and more users included every day. So what's happening is unless the conversion rate is really is converting at a very high rate, essentially it's going to keep dropping, and that's what's happened. So if we take the example of day 9, for instance, you'll see that group A users were 270,000 and group B were 24,900. And um, so in fact, sorry, so yeah, that was the number of users, and the number of conversions in group B is 28,050, and in this case it is 24,900. So the conversion rate in these two cases, in both cases of course the number of users is 270,000. So you'll see that the conversion rate is this 0.09 and zero point 0.1 in B, and therefore the lift, the the cumulative lift is 12.7%. So if I go back to that curve here, you'll see that 12%, 12.7%, there it is somewhere around here, is actually much lesser than the first day's conversion rate, because that was the first day of the experiment, right? So there is nothing, the cumulative is that very day's data is equal to that, because nothing else, no prior or past data has been pulling down the average. So essentially it has a pull down effect, the cumulative averaging in this case. So that's why we see that if you just take the decision of stopping the experiment and take that at face value, that lift that you're getting here, the lift is very high, as you can see, which is above 20%. You'll think that okay, this experiment has really worked, and you will act on that. You will take the decision based on this observation, but it will be wrong even though sample size was reached and statistical significance was reached. So this was my whole point. You have to take into account, for instance, the day of the week effect. You have to continue this experiment for a while, and especially take into account local maxima minima, local seasonalities, over different phases and periods of time. So this is an important element of seasonality that you have to take into consideration, which is at least day of week effect you should take. So minimum of 8 days you should be running a test for. The reason I say 8 is because the test sometimes takes 1 or 2 days. An effect sometimes takes 1 or 2 days more, right? So if you have an effect, suppose you start on Sunday, you go on to the next Sunday, maybe the effect of Sunday is not going to be fully felt. So maybe you should also have a post test window, which in this case can be just say 1 day or 2 days. So that is how you should organize your experiment. Don't stop too early. That will also have its negative consequences, and it will adversely affect your decision making. Hope this was useful. I did not walk into every aspect of the mathematics here, but I guess the idea was clear from it, from the graph. And you'll see that there's also a graph for p-value that I haven't showed, but essentially it started from being statistically significant, pretty much stayed flat, and then it actually became even better, right? Even though the lift actually dropped, because over time obviously what happens is it becomes more and more statistically significant, and that's very realistic even though it's a simulated data. So the real lift, as you can see, even though it was statistically significant earlier, it actually became even more significant in a sense. I mean, of course, significance doesn't have any level in a sense. As long as it's just less than 0.05, it's fine for a 95% confidence interval, for a 5% level of significance. But yeah, I mean, uh, as you can see, for a much lower lift, the statistical significance is much higher when we actually consider the next weekend as well. So this actually stabilizes over time, and you'll see that the true effect is somewhere around this line, this green dotted line here, the true average lift. Okay, and that actually has been provided, that true lift we know in this case because it's a simulated data. That's how we have defined the model itself, I mean the entire setup itself, the experiment. So that's why we know that the true lift is at a certain point, and we see that the effect is much clearer. The lift is actually much closer to the real average true lift over time, and it's definitely way higher than that at the start of it. So that was the overall idea. If you have any questions, do let me know in the comments, and thanks for watching. I'll see you in the next video.